Hello everyone and welcome back once again to the JCE Connect. And in today's session we are going to discuss the continuation of design of built up column, that is built up column consisting of two channel sections placed back to back. So in the previous session we had discussed about how to select a section from sheet table, and even we calculated the design compressive load of two channel sections placed back to back, and we refer the different clauses like for the slenderness ratio lambda, for built up section, for laced columns. Okay, and we got to know that our section is safe to carry the design compressive load. Okay, so the selected section is safe to carry the load. Up to that we have covered the last session. Okay, so in this session we are going to discuss about the design of lacing. Okay, so in built up column, as I told you in the previous session, and even I shown you the different types of lacing systems in compression member. So in this session also I will just overview and I will just show you the built up sections, how the built up sections is designed. Okay, the sketch of the built up section. Here this part I have covered already, I have discussed in the previous session, but still. Okay, so we can see here a built up section with a single lacing and built up section with double lacing, and again we have the built up section with the lacing plus the plates, additional plates. Okay, so in this we are going to design this system, that is for single lacing system. Okay, so I have represented that in our sketch. Okay, so just I'll explain the components of our two channels placed back to back. Okay, so you can see these are plates, are nothing but lacings. Okay, are nothing but lacings, and we have the two channel sections with the spacing of 260 mm face to face, that is back to back. Okay, so here the inclination of the plates we are assuming at 45 degree, and this is A1 and this is B. Okay, this is A1 and this is B1. Sorry, this is as B1, A1 and B1. Okay, then this is as the edge distance, or G. Okay, so here we'll continue with the session now. Okay, so this A1 is nothing but the spacing between the vertical distance between the two lacings, the single lacing. Okay, this is the horizontal distance. Okay, now assuming the inclination of lacing is equal to 45 degree. Okay, we'll assume the inclination of lacing as 45 degree. Okay, so this is again, I'll note down the clause as per 7.6.4 page number 50, as per 7.6.4 page number 50. Okay, understood. So I'll just show the clause. So we'll go to page number 50. Okay, here you can see the clause 7.6.4 angle of inclination. Okay, the lacing bars, whether double or single system shall be inclined at an angle not less than 40 degree, not more than 70 degree to the axis of built up member. Okay, so here the angle of inclination should not be less than 40 degree and should not be more than 70 degree. So we have selected the inclination of built up section, that is for plates we have selected 45 degree. Okay, so therefore you have to refer this clause for that. So B1 is equal to, so what is B1 is equal to, what is B1 here? B1 is equal to S plus 2 times G. So that is, what is, this is S plus 2 times G, S plus 2 times G. So here G is equal to gauge distance, G is equal to gauge distance, so that we can assume 50 mm to 60 mm. We can assume gauge distance equal to 50 mm to 60 mm. So we will take gauge distance equal to 60 mm. We will take gauge distance equal to 60 mm. So therefore B1 is equal to S plus 2G, S plus 2G. So S is 260 mm plus 2 times 60. Okay, so that is B1 is equal to 380 mm. So we got B1 is equal to 380 mm. Okay, now this is horizontal distance. Now vertical distance, vertical distance between the center of bolts, between the center of bolts. Okay, that is A1 is equal to 2 times B1, that is A1 is equal to 2 times B1. Why? Because see, because when the angle is 45 degree, this height should be equal to this height. So according to that, so that is A1 is equal to 2 times B1, because of angle of inclination is 45 degree. So that is 2 times 380, so is 760 mm. So A1 is equal to 2 times B1, 2 times 380, 760 mm. Okay, so as per clause number 7.6.5, 7.6.5.1, page 50, the maximum slenderness ratio of the maximum slenderness ratio of the components of the main member the maximum slenderness ratio of the components of the main member, that is A1 by R1, should not be more than 50 or 0.7 times lambda actual. Okay, so the maximum slenderness ratio of the components of the main member A1 R1 means the components, means these are the components, the lacings are components. Okay, so उन्होंने क्या दिया है, the maximum slenderness ratio, the maximum, according to this clause, the maximum slenderness ratio of the components of the main member A1 by R1. So A1 is this height, so A1 is this height. Okay, A1 by R1 should not be more than 50 or 0.7 times the actual slenderness ratio. Okay, okay, so where R1 is equal to R minimum for channel section, R minimum for channel section. So for R minimum for channel section, we will get it from steel table, that is RYY. So we have got it is 28.3 mm. RYY for channel section, it is R minimum, that is 28.3 mm. So therefore A1 by R1, so A1 is 760 divided by R1 is 28.3, which is, we'll get it as 26.85. So I'll check. So 760 divided by 28.3, so we'll get it as 26.85, which should not be more than least of following, that is, first is 50 mm, second one is 0.7 times the lambda actual. So we have got the lambda actual is 81.56. We have got the lambda actual as 81.56. So this will get it as 57.09. Okay, so the least of these two means 50, and okay, the least of these two is 50 mm, and our slenderness ratio of the component is again less than, this should not be more than this least of these two, which is 50 mm. So again it is less than this. Okay, so therefore okay because least of these two is 50 mm, and our slenderness ratio is 26.85, which is less than 50 mm. So therefore okay. I'll show you the clause now. It is on page number 50. If it is possible, I'll show you on page number 50. Okay, here it is given as here it is given that clause. The maximum spacing of lacing bar where connected by bolting, riveting, welding shall also be such that the maximum slenderness ratio of the components of the main member A1 by R1, whereas consecutive lacing connection is not greater than 50 mm or 0.7 times the most unfavorable slenderness ratio of the member as whole, means for the whole section, that is two channel section placed back to back, उसके लिए should be less than that. And we have got it is safe where R1 is minimum radius gyration of individual member being laced together. Okay, so we have got it is less than that, so therefore okay. Now next is size of lacing plate after design of lacing. So here it is size of lacing plate. Okay, size of lacing plate. Okay, so here length of the plate is B1 square plus A1 by 2 square. Okay, so that is B1 is 380 plus 760 by 2 square, so that is 537.4 mm. So that is length of plate. How it is, I'll show you. Okay, I'll show you here. You can see here. So the length of the plate is A1 by 2, because it's 45 degree, A1 by 2 B1, A1 square plus B1 square, square root of A1 by 2 square plus B1 square. So we will get the length of lacing plate. Okay, then next is thickness of lacing plate. First is length, second one is thickness of lacing plate. Okay, thickness of lacing plate. So again, as per 7.6.3 page 50, you have to find out again. So it is given as T1 is equal to 1 by 40 times L1. Okay. So L1 is here. T1 is equal to 1 by 40 times L1. So it is 1 by 40 times L1. So that is 537.4. So we'll get it as 13.43. So we'll 13.43. So we'll round figure to T1 is equal to 14 mm. So the thickness of lacing plate, we have to provide a plate, and that thickness of is, we have got it as 14 mm, and that clause is again we have to refer page number 50. I'll just show you. Okay, so here it is given as thickness of lacing bar. You can see the thickness of lacing bar. The thickness of flat lacing bars, flat means plate lacing bar, shall not be less than 1/40th of its effective length for single lacing and 1/60th of effective length for double lacing. Okay, so it is, we have taken as single lacing, so that's why it is 1/40 times the length of lacing bar. Next is after thickness, width of lacing plate. Next is, third one is width of lacing plate. Width of lacing plate. So again, as per 7.6.2 page 50, as per 7.6.2 page 50, B minimum width of the lacing plate, that is minimum, that is 3 times the nominal dia of bolt, 3 times the nominal dia of bolt. So therefore, assuming dia of bolt is equal to 20 mm, assuming dia of bolt is equal to 20 mm, so therefore B1 is equal to 3 times 20, so we will take it as 60. So therefore the width of lacing plate is 60 mm. Okay, so again, by referring the same clause, page number 50, I'll just show you width of lacing plate. You can see width of lacing bar. In bolted riveted construction, the minimum width of lacing bar shall be 3 times the nominal diameter of end bolt or rivet. Okay, as per the clause number 7.6.2 page number 50, width of lacing bar. So we have taken 3 times the diameter. So we have assumed diameter is equal to 60 mm. So therefore, provide a lacing plate of size 60 mm by 14 mm, 16 mm, 40 mm. Okay, now as per 7.6.6.3 slenderness ratio of lacing plate, slenderness ratio of lacing plate, lambda lacing is given by KL by R minimum, which should not be more than 145, which should not be more than 145, where KL is equal to, because the effective length factor for plate, we will take it as 1 because it is connected directly to the main member center to center by using bolts. So 1 times 537.4, which is equal to again 537.4 mm. Okay, that is KL. then R minimum is list of again RXX and RYY of plate, RXX and RYY of plate. Okay, so now here we have the plate we have provided like this. Okay, we have provided a plate, and if you see the cross section of this plate, okay, it is 60 mm plate, width of the plate is, and if I see the cross section, if I cut, the plate will be like this. This is 60, the thickness is 14, okay. So here we have to find out the moment of inertia about IXX and IYY to get the minimum radius of gyration. So for plate, IXX is BD cube by 12, so that is 14 into 60 cube by 12, and IYY is about horizontal axis, it is I, so this is IXX, XXX6, this is YYX6, so about horizontal axis IXX is BD cube by 12, so 14 into 60 cube by 12, and IYY is DB cube by 12, so 60 into 14 cube by 12, okay. So we'll get these two values as IXX and IYY, because see, with respect to vertical axis, parallel is B, so BD cube by 12, and with respect to horizontal axis, parallel is B is 14, so BD cube by 12 and TB cube by 12, so that is okay. So we'll get these values are 252 point, okay, 252 into 10 to 3 mm raised to 4, and this value as 13.72 into 10 to 3 mm raised to 4, okay. So therefore I minimum is least of these two, so that is 13.72 into 10 to 3 mm raised to 4, okay. So we got I minimum, so therefore, okay, so here therefore therefore R minimum is equal to square root of I minimum by area, okay. This is a basic formula, R minimum, square root of I minimum by A. So I minimum is, we have put it as 13.72 into 10 to 3, and area is 60 mm by 14 mm, okay. So we'll get it as R minimum is equal to, I'll just check, so it is 13.72 into e raised to 3 divided by 60 into 14, okay. So we'll get as 4.04, so we'll get it as 4.04 mm, okay. So this is regarding R minimum. Then, so therefore lambda for lacing is equal to KL by R minimum. So K is 1, L is 537.4, R is 4.04, so which is 132.98 mm, which is less than 145 mm, okay. So as I told you, this should not be more than 145 mm, okay. I can show here the slenderness ratio KL by R, the lacing bar shall not exceed 145 mm. So just now we have calculated, okay. So next is you have to check for compressive strength, check for compressive strength. Check for compressive strength. Check for compressive strength as per again clause number 7.6.6 slash 7.6.6.1, page number 50. Okay, page number 50. So just I'll show it is okay, page number 50, 7.6.6.1. okay, 7 point, okay, here it is given as that clause. Okay, here the lacing shall be proportion to resist total transverse shear Vt at an point in the member equal to at least 2.5% of axial force in the member and shall be divided equally among all the transverse lacing system in the parallel planes. Okay, it is given as, okay, so we have to find out the transverse shear first. Okay, the transverse shear. Okay, so I'll just show it here. So we have the two lacings like this, just show. We have the lacing like this. Okay, we are putting lacings like this. Okay, and we have to find out the transverse shear. So that is the shear transferred like this. So that is Vt by n. Okay, the transverse shear Vt divided by n means the number of plates. Okay, so therefore, and the angle is, this angle is 45 degree. Okay, so therefore transverse shear in each panel is equal to Vt by n. So Vt is equal to, again it is as per clause, 2.5% of Pu is given. It is, we have to take 2.5% of the axial force. So 2.5 times 1600 divided by 100, so that is 4%. So we will get Vt is equal to 40 kilonewton. So then, so therefore Vt by n, so that is 40 by, at the joint we have the two lacing plates, so that is 20 kilonewton. At the joint we have the two lacing plates, so that is Vt by n. Okay, so therefore compressive force in each panel, so that is the compressive force in each panel. So this is the compressive force. Compressive force in each panel is given by, so we have to find the component, because it is horizontal, we have to find the component. So we will get that as Vt by n cosec theta. Okay, so that is Vt by n is 20 into cosec theta, so that is 20 into cosec theta is 1 by sine 45, 1 by sine. Okay, so we will get this force Fe in the, or the transverse, the force is 28.28 kilonewton. Okay, so we got this force as 28.28 kilonewton. So that is Vt by n into cosec theta, so is equal to 20 into cosec theta. So 20 into cosec theta and then 1 by sin theta, so that is 28.28 kilonewton. Okay, so now we have, lambda is equal to, for lacing, lambda lacing is equal to KL by R minimum we already calculated, that is 132.98. okay, 132.98. So again, for buckling class C, for buckling class C, okay, because again the plate is in buckling class C, plate is again buckling class C. So for lambda 132.98 buckling class C, so and Fy is equal to 250 Newton per mm square. Okay, so we'll get PCD is equal to FCD into area. Okay, so you have to refer the buckling class C, that is table number 9C. Okay, and for Fy 250 Newton per mm square, so we have to find out the FCD. So FCD will get it as 71.86 into area is 60 into 14 for plate. So this will get it as 60.36 kilonewton, which is more than 28.8 kilonewton. So therefore okay. So again the buckling, so it is safe against buckling. Okay, so the plate what you are going to provide in lacing, that plate is also safe in buckling. Okay, the plate what you are going to provide this plate, again ultimately we got it is safe in buckling. Okay, that is again buckling and design coercive strength. Okay, so next is design of connection. Next is design of connection. Okay, because we are not at design connection, so we assumed the 20 mm dia bolts. So therefore assuming 20 mm dia bolts, 20 mm dia bolts of PC 4.6. So here we have to find out again the design strength of bolt, design strength of bolt. So that is least of shear strength and bearing strength. You have to find out the shear strength and bearing strength. So by this you will get the design strength of bolt BB is equal to 45.27 kilonewton. We have to find out that. Okay, I am not going to calculate again. So we have to find out that. You people have to find out that. So that is 45.27 kilonewton. So therefore number of bolts is equal to force divided by bolt value, force divided by bolt value. So here the force is 28.8 in each plate divided by bolt value is 45.27. so we'll get it as 0.63. so we have to provide one number minimum. Okay, so we have to provide a lacing system with one number of bolt for connection. Okay, so this is regarding design of the built up sections consisting of two channels placed back to back with a spacing of 260 mm and designed with a single lacing system by using a plate of size 60 mm width and 40 mm thickness. Okay, so and again we have to design connections also for that. Okay, so this is regarding today's session. Okay, thank you very much.